March 15, 1944. Outside the industrial city of Kassel, a captured American medium tank sat in a testing facility surrounded by some of the most accomplished engineering minds in Europe. The engineers from Henschel and Krupp believed they were about to dissect another example of crude Allied machinery, something they could dismiss with the same contempt they had shown for earlier American designs. They had no idea they were staring at a revolution in military thinking that would fundamentally challenge everything they understood about armored warfare. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What these engineers discovered over the following weeks would shake their confidence more than any battlefield defeat. The Sherman tank, which they expected to tear apart in hours, would reveal a philosophy so alien to their precision-crafted approach that it bordered on genius. A machine designed not for the specialists who built it, but for the ordinary soldiers who would have to keep it running under the worst conditions imaginable. Dr. Heinrich Forster adjusted his spectacles and walked slowly around the M4A3 Sherman that had been transported to the facility 3 days earlier. The tank had been captured intact near Anzio in Italy, abandoned by its crew after mechanical difficulties during a chaotic engagement. Forster, who held 2 engineering degrees and had spent 12 years designing components for Germany's most sophisticated armor, approached the vehicle with barely concealed disdain. He had examined Soviet tanks before, crude things welded together with an almost insulting lack of refinement. He expected something similar from the Americans, perhaps slightly better finished, but ultimately another example of mass-produced mediocrity. The Sherman certainly looked ordinary enough, its boxy hull and riveted construction lacking the intimidating presence of German designs. Beside him stood his colleague, engineer Klaus Brenner, a man who had worked on the Tiger's transmission system and took considerable pride in the complexity of that achievement. Brenner carried a leather notebook where he meticulously recorded technical observations, a habit that would serve him well over the coming investigation. Also present was Sergeant Otto Schreiber, a tank recovery specialist who had been pulled from frontline duties specifically for this examination. Schreiber had spent 3 years retrieving damaged vehicles from battlefields, often under hostile conditions, and he understood the practical realities of armored warfare better than any laboratory engineer. His weathered hands and oil-stained uniform marked him as someone who lived with machinery, rather than merely studying it. The 4th member of their team was technical specialist Maria Hoffmann, one of the few women working in Germany's military-industrial complex. She had fought for years to be taken seriously in a male-dominated field, and her expertise in metallurgy and materials science had finally earned her a place in critical assessments. She approached the Sherman with neither contempt nor admiration, only a scientist's curiosity about what they would find. Forster ordered the tank moved into the main examination bay, a vast hangar-like space equipped with overhead cranes, cutting tools, and diagnostic equipment. The Sherman was positioned under bright floodlights, every surface suddenly visible in harsh detail. Workers began documenting external features, measuring armor thickness, examining track links, photographing mechanical connections. The first surprise came within minutes. Brenner had removed an access panel on the hull, expecting to find it secured with specialized fasteners, requiring unique tools. Instead, he found himself staring at standard bolts that could be removed with common wrenches. He frowned, checked his tools, and removed another panel. Same result, and another. Every access point used the same standard sizes. "Tell me later," Forster said when Brenner tried to point this out. "Let us do a complete external examination first." But as they worked around the vehicle, the pattern repeated itself. Track tension adjusters used standard tools. Engine deck fasteners required no special equipment. Inspection ports opened with simple latches. Schreiber, the recovery sergeant, found himself increasingly puzzled. He had worked on German tanks, where accessing certain components required custom-made wrenches, and where field repairs often became impossible because the necessary specialized tools were unavailable. By the end of the first day, they had compiled an extensive photographic record and removed several external components. The team gathered in Forster's office to review their initial findings. Maps of the eastern and western fronts covered one wall, showing the extent of territory Germany had lost over the past year. Production charts on another wall documented the declining output from factories increasingly targeted by Allied bombing. "Gentlemen," Forster began, "and Miss Hoffman," he added with a nod to the metallurgist, "we have examined the external features of this American tank. Tomorrow we will begin internal inspection. I expect we will find crude construction methods, low-quality materials, and unsophisticated mechanical solutions. The Americans have neither the engineering tradition nor the manufacturing precision of German industry." Hoffman raised her hand slightly. "Dr. Forster, I took samples from the armor plate today. The welding quality is actually quite consistent. The steel composition appears carefully balanced for a combination of hardness and ductility. These are not the marks of crude work." Forster waved this away. "Surface impressions, Miss Hoffman. Wait until we examine the engine and transmission. That is where we will see the true limitations of their manufacturing capability." "But Schreiber," the sergeant spoke up quietly, "Sir, I noticed something today. Every bolt we removed was the same size. Every panel we opened used the same fasteners. In the field, this would mean a crew could carry minimal tools and still access any part of the vehicle." "This is not a virtue, Sergeant," Brenner interjected. "It suggests a lack of optimization. Different components require different fastener strengths. Using universal sizes means either over-engineering some connections or under-engineering others. It is wasteful and imprecise." "Or practical," Schreiber said, then fell silent under Brenner's sharp look. The next morning they began the process of accessing the Sherman's internal systems. The engine deck opened easily, revealing the Continental R975 radial aircraft engine that powered the tank. Forster expected a difficult process of removing numerous components to access the engine itself. Instead, he found that the entire power plant could be extracted as a single unit. Brenner examined the engine mounting system with growing confusion. The Americans had designed the installation so that 4 men with standard lifting equipment could remove the complete engine in under 2 hours. He had worked on tanks where engine replacement required specialized facilities and took several days. This seemed impossibly simple. "Look at this," Hoffman called from the other side of the vehicle. She had opened a compartment revealing ammunition storage. The shells were arranged in racks that allowed quick access, with clear markings indicating quantity and type. The fire suppression system was equally straightforward, with clearly labeled controls that required no technical knowledge to operate. As they worked deeper into the vehicle's systems, a disturbing pattern emerged. Everything was accessible. Everything was labeled. Everything could be maintained with basic tools. The electrical system used color-coded wiring that made tracing connections simple. The fuel system had easily replaceable filters at logical access points. The transmission, which Brenner had expected to be the weak point, was designed in modular sections that could be serviced independently. By the 3rd day, Forster's confidence had begun to crack. He stood in front of the partially disassembled Sherman, watching Schreiber demonstrate how a relatively inexperienced crew could replace a damaged final drive using only the tools carried on the tank itself. The process took less than 3 hours and required no specialized knowledge beyond what could be taught in a brief training session. "This cannot be effective," Forster insisted. "They have sacrificed performance for simplicity. The engineering is too basic." Hoffman handed him a metallurgical report. "Sir, I have analyzed samples from multiple components. The steel quality is excellent. The casting processes show sophisticated quality control. The armor, while not as thick as our heavy tanks, is well designed for its intended purpose. There is nothing crude about this vehicle's construction." Brenner added his own observations. "The engine produces 350 horsepower from a design that is already in mass production for aircraft. They are not developing custom power plants for each vehicle. They are using proven, reliable engines that can be manufactured in enormous quantities with existing tooling. The transmission is not as sophisticated as ours," Brenner continued, "but it has fewer failure points. The suspension is simple but effective. The tracks are basic but durable. Every system prioritizes reliability and maintainability over maximum performance." Schreiber, who had been listening quietly, finally spoke. "Sirs, in the field, mechanical sophistication is often a liability. I have recovered countless vehicles that were abandoned, not because they were damaged beyond repair, but because the repairs required equipment or expertise that was unavailable. This American tank, he gestured at the Sherman, could be kept running by ordinary soldiers with basic training. Forster felt a cold sensation in his chest. He walked to the wall where production charts hung, showing Germany's tank output. In 1943, German factories had produced approximately 6,000 armored vehicles of all types. The numbers were declining as Allied bombing intensified. He had heard intelligence estimates suggesting the Americans were producing Sherman tanks at a rate of over 1,000 per month. He had dismissed these figures as impossible exaggeration. Now, looking at the Sherman's design philosophy, he realized they might be conservative estimates. The Americans had not tried to build the perfect tank. They had built a good enough tank that could be manufactured in overwhelming numbers and kept operational by ordinary crews under combat conditions. Over the next week, the team conducted operational tests. They had found technical manuals with the tank, written in clear language with extensive illustrations. Hoffman, whose English was excellent, translated them and was struck by their accessibility. These were not technical documents for specialists. They were training materials designed for young men who might have been farmers or factory workers months earlier. The manuals included troubleshooting guides that walked crews through common problems using simple yes or no decision trees. If the engine will not start, check fuel supply. If fuel supply is adequate, check electrical connections. The approach was systematic, but required no deep mechanical knowledge. Brenner spent an entire afternoon studying the Sherman's fire control system. It was not as precise as German optics, but it was adequate for most combat ranges. More importantly, the sights were rugged and maintained accuracy even after rough handling. The gun stabilization system, while simple, allowed firing while moving with reasonable accuracy. German tanks generally had to stop to shoot effectively. The more they studied, the more uncomfortable the conclusions became. Schreiber conducted a simulated field repair exercise, deliberately disabling several components and then repairing them using only the tools and spare parts stored on the tank itself. He completed repairs that would have required specialized facilities on a German vehicle. They examined the crew ergonomics and found another revelation. The interior was relatively spacious, with clearly defined positions for each crew member. The commander had excellent visibility through a cupola with multiple vision blocks. The radio equipment was simple to operate and remarkably reliable. Every control was positioned for ease of use rather than mechanical optimization. "Sir," Schreiber said during one of their evening review sessions, "I have been thinking about crew efficiency. In this tank, a well-trained crew could operate for extended periods with minimal fatigue. The seats are adjustable. The ventilation is good. The ammunition is within easy reach. These seem like small things, but they matter during long operations." Maria Hoffman had conducted a comprehensive materials analysis, and her findings troubled everyone. The Sherman's armor was not as thick as German heavy tanks, but the quality of the steel was excellent and the construction methods were sound. The vehicle was not heavily armored because the Americans had made a conscious choice to prioritize mobility and reliability over maximum protection. Even more concerning was her analysis of the manufacturing processes. The Sherman used a combination of casting, welding, and assembly techniques that were highly suitable for mass production. German tanks, with their precision-machined components and complex assemblies, required far more labor hours to build. "Gentlemen," Hoffman said during her presentation, "I estimate this tank requires approximately 10,000 labor hours to manufacture. A Panther requires approximately 150,000 hours. A Tiger, over 300,000. The Americans have optimized for production efficiency." Forster felt the walls closing in. He understood now what they were facing. Germany had the most sophisticated engineering in the world, the most advanced metallurgy, the most precise manufacturing, and they were losing to an enemy that had deliberately chosen good enough over perfect. The final report took several days to compile. Forster knew it would be controversial, potentially dangerous to his career, but scientific integrity demanded honesty. He wrote carefully, knowing his words would reach the highest levels of military leadership. The M4 Sherman medium tank represents a fundamentally different design philosophy than German armored vehicles, he began. Where German engineering prioritizes maximum capability and sophisticated solutions, American engineering prioritizes reliability, maintainability, and manufacturing efficiency. He detailed the findings systematically. The engine could be replaced by a crew in the field. The transmission was simple but durable. The suspension was basic but effective. Every component was designed for easy access and repair. The entire vehicle could be maintained with standard tools requiring minimal specialized training. Most significantly, he wrote, "This tank can be produced in vast numbers." The Americans have sacrificed some performance capabilities to achieve manufacturing simplicity. This trade-off makes strategic sense for a nation with enormous industrial capacity. Brenner contributed a section on comparative production efficiency. His calculations were devastating. For every German heavy tank produced, the Americans could manufacture approximately 15 Shermans using similar resources. The quality gap between vehicles was far smaller than the quantity gap. Hoffmann's metallurgical analysis filled several pages. She concluded that while German armor steel was marginally superior, American steel was more than adequate for its intended purpose. The manufacturing consistency across multiple Sherman hulls she had examined was remarkably high, suggesting well-controlled production processes. Schreiber wrote the section on field maintainability, drawing on his 3 years of recovery operations. A German tank that suffers mechanical failure in combat often becomes a permanent loss, he wrote bluntly. We lack the specialized equipment, tools, and replacement parts to repair vehicles in forward areas. Many vehicles that could be fixed are abandoned because field repairs are impossible. The Sherman, he continued, is designed from the beginning to be maintained by its crew. The tools are standard, the procedures are simple, the components are modular. An American tank crew has a much higher probability of keeping their vehicle operational throughout extended operations. The report included dozens of technical drawings, photographs, and detailed component analyses. The conclusion was inescapable. The Sherman was not a better tank than German designs in terms of pure performance. It was a better tank in terms of strategic utility. Vorster presented the report to his superiors in early April. The meeting did not go well. Senior officers, many with engineering backgrounds themselves, initially rejected his conclusions. They pointed to combat reports where single German heavy tanks had engaged multiple Shermans successfully. They cited the superior armor and firepower of German designs, but Vorster held firm. Yes, sir, a Tiger can engage 5 Shermans and potentially prevail. But the Americans can produce 15 Shermans in the time we produce 1 Tiger, and if the Tiger suffers mechanical failure, which happens frequently, it often cannot be repaired in the field. The Shermans keep running. One general stood and angrily declared the report defeatist. You are saying we should copy American simplicity, abandon German engineering excellence? No, sir, Vorster replied quietly. I am saying we have optimized for the wrong variables. We built the most sophisticated tanks in the world. The Americans built tanks that serve their strategic needs. There is a difference between technical achievement and military effectiveness. The room fell silent. Everyone present understood the implications. Germany's vaunted engineering superiority, the pride of the nation's industrial identity, had become a strategic liability. Precision required time, complexity required specialists, sophistication required resources, all things Germany had in diminishing supply. In the months that followed, the report circulated through military and industrial planning offices. Some dismissed it entirely. Others found its conclusions deeply troubling, but difficult to refute. A few forward-thinking officers began asking uncomfortable questions about German production priorities. Brenner found himself transferred to a different project, working on simplified tank designs that never entered production. The war situation was deteriorating too rapidly for major industrial reorganization. Hoffmann continued her metallurgical work, occasionally sharing quiet observations with colleagues about the American approach to engineering problems. Schreiber returned to frontline recovery operations. He noticed with increasing frequency how many German tanks were abandoned due to mechanical failures that should have been repairable. He thought often about the Sherman sitting in the Kassel facility, with its standardized bolts and accessible engine. Vorster remained at the testing center, examining other captured Allied equipment. Every analysis reinforced his conclusions. The British, Americans, and even Soviets had all chosen reliability and production efficiency over maximum performance. They had correctly identified that modern industrial warfare was ultimately about logistics, manufacturing capacity, and keeping equipment operational under field conditions. By late 1944, American production had reached staggering levels. Over 49,000 Sherman tanks would be built during the conflict, along with countless variants. German production of all tank types barely exceeded 25,000 vehicles for the entire duration of hostilities. The numbers told their own story. But the real difference lay in those details Vorster's team had documented so carefully. The Sherman crews, who could replace an engine in a muddy field using basic tools. The simplified training that allowed rapid crew replacement. The standardized parts that meant vehicles could cannibalize components from damaged tanks. The reliability that kept units operational during extended campaigns. German tankers, fighting in sophisticated machines that required specialized maintenance, increasingly found themselves abandoned by their own vehicles. A Panther with a broken transmission often became a pillbox, its crew waiting for recovery equipment that never arrived. A Tiger with engine problems sat disabled, its awesome firepower useless, because field repairs were impossible. Vorster saw reports from the Eastern and Western fronts describing American armored divisions that maintained operational readiness rates above 70% even during continuous combat operations. Comparable German units often fell below 30% readiness due to mechanical failures and supply difficulties. The irony was bitter. German engineering had created technological marvels, masterpieces of mechanical sophistication, but the Americans had created something more valuable for actual warfare: reliable, maintainable, producible vehicles that ordinary soldiers could keep running under terrible conditions. In his private moments, Vorster thought about the philosophical implications. Germany had approached tank design as an engineering challenge. Create the most capable vehicle possible. America had approached it as a system design challenge. Create a vehicle that serves the complete operational system, from factory floor to battlefield maintenance. One evening in December 1944, as Allied armies closed in from east and west, Vorster sat in his office reviewing production statistics one final time. The numbers were stark. American industry had produced more tanks in 1944 alone than Germany had built in the previous 3 years combined. And American tanks were running while German tanks sat disabled for want of specialized parts, tools, or expertise. He thought about the Sherman in the testing bay, that ordinary-looking vehicle with its revolutionary simplicity. He had been so certain, that first day, that it represented crude American manufacturing. Now he understood it represented something far more sophisticated, engineering that prioritized real-world utility over technical elegance. The lesson was profound and arrived far too late to matter. Germany had the better engineers, the more advanced metallurgy, the superior precision manufacturing. But America had understood something more important, that engineering excellence must serve strategic purpose, and in modern warfare, that purpose is best served by reliability, maintainability, and overwhelming numbers. Maria Hoffman, in one of their last conversations before the facility was evacuated ahead of advancing Allied forces, summarized it perfectly. "We built tanks for engineers to admire," she said quietly. "They built tanks for soldiers to use. There is your difference. The Sherman that started this revelation was eventually destroyed during an air raid that damaged much of the Kassel facility. But the knowledge gained from its examination remained with the surviving team members for the rest of their lives. They had witnessed a fundamental truth about industrial warfare, that the perfect can be the enemy of the good, and that genius sometimes lies in deliberate simplicity." After the conflict ended, Vorster found work in the civilian automotive industry. He carried with him the lessons learned from dissecting that American tank. In his later years, he occasionally lectured at engineering schools. always emphasizing the importance of design for maintainability, standardization, and real-world operational requirements. He would tell students about the day he opened a Sherman tank expecting to find crude American work, and instead discovered a masterclass in practical engineering. He described the moment he realized that using standard bolts throughout the vehicle was not a sign of poor design, but rather brilliant design for a different set of priorities. The story of what happened when German engineers studied a Sherman tank became a case study in how assumptions about superiority can blind us to alternative approaches. It illustrated how technical sophistication, without consideration for practical implementation, can become a strategic weakness, and it demonstrated that sometimes the most profound engineering insight is knowing what not to over-engineer. For Schreiber, who survived to old age, the memory remained sharp. He had pulled countless German tanks from battlefields, magnificent machines abandoned because they could not be repaired in the field. He had seen the contrast with American vehicles that kept running despite rough handling and minimal maintenance. The difference, he knew, was not in the capability of the machines, but in the philosophy that created them. The Sherman was not invincible. It had limitations and vulnerabilities that cost many crews their lives, but it embodied a truth that Germany learned too late, that in industrial warfare, the army that can keep its equipment running wins, and that simplicity of maintenance is as important as sophistication of design. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.